Okay, let's see. Hi. Can you hear me? I'm sorry this stupid thinking this. It didn't do this to me last year. Just trying to share the link out again. Oh my goodness. I'm sorry. This is such a pain in the neck. Ay. Okay. Let's give it another minute or so. Third time's the charm. Let's hope. I really would like to finish this test at a reasonable hour. We have 3 hours for this Regents. Yes. Test is 3 hours. 3 hours. Realistically, I think you only need like 2.5. Okay. We were in the middle of doing percent error. Goodness gracious. Okay, so you wind up getting 0.1 over 2. I don't know what 0.1 over 2 is equal to. So you would do 0.1 divided by 2. Take this number, multiply it by 100. You would wind up getting 5% error. The 2 on the bottom is the science number. That's the accepted value. We got that from the table. Okay. That is everything for that section. So we're going to move on. Okay. And we did 50 already. Okay. Moving right along. Okay. 57. We are given an equilibrium reaction for SO2, O2, and SO3. The reaction can be catalyzed by either vanadium or platinum. Compare the rate of the forward to the rate of the reverse. We know this is equilibrium because your rates are equal. Your concentrations stay constant. So 57, one word, equal. 58, state how the equilibrium shifts when SO3 is removed from the system. So this is our beautiful Le Chatelier's principles, where we have our equation 2SO2 and O2 becoming 2SO3. Now, this is saying that I'm going to remove SO2 from the system. So we are reducing the amount of this. So we have our Le Chatelier's rules: add, away, and take toward. So when we add to the system, so say we added SO3, say we added it, we would shift away from the SO3. When we take SO3 out, we shift toward the SO3. If I remove this, I want my concentrations to stay constant. So for like a split second, these compounds or compound and element are going to start breaking apart so that we can form more SO3 and get it back so that we can get back to everybody being equal again. So we are going to take toward, if you take something away, you have to shift toward that thing. So because this is on the right side, we would shift right. Nice job, Jared. State how the equilibrium shifts. You could just say shift right. That simple. No problem, Jared. Just don't mess it up tomorrow. Check your work. Okay. 59. A potential energy diagram for the forward reaction is shown in your booklet. Okay, so I don't have the booklet in front of me, but I can tell you that I know it would look like this. On this diagram, draw a dashed line to show the potential energy changes. How the potential energy changes when a reaction is catalyzed. Now, this was literally a test question on your equilibrium test. And we kind of went over this a little bit earlier. This energy right here is the energy of your reactants. This is your products. The distance between from here to here, that's delta H. The answer to this question is going to be the purple dashed line I'm about to add. That is going to be this right here. So what happens? Without this catalyst, my reaction needs, let's see, I need another color. Red. Without this catalyst, my reaction needs that much energy to get started. When I add the catalyst, it only needs that much energy to get started, just that little purple arrow. So what happens is my activation energy decreases. And as my activation energy decreases, my reaction happens more easily. That's the point of a catalyst. So you would draw that type of line. Going through this, because the energy is a product, that means it's coming out of the reaction, meaning the energy is exiting. This would be exothermic. This roller coaster would be exciting. Exothermic. Okay. Is everyone good so far? We can move on to the organic section. Because nobody's commented in a hot minute. Okay, good. I get nervous, like the whole thing froze or something. I'm having bad luck with this. Yes, the catalyst is a shortcut. Great job. Okay, here we go. We got two compounds. We know they're organic. Now, explain in terms of bonding why compound A is saturated. Now, saturated has two definitions in chemistry. First one is a saturated solution, which means that the solution can't hold any more solute, and your solute starts to sit on the bottom. A saturated molecule means that it is full of hydrogens. So if it's a solution, it's full of solute. If it is a compound, it is full of hydrogens. So for this particular question, it says explain in terms of bonding. So you have to talk about bonding here. You would have to say something along the lines of all of these carbons have single bonds to each other. All of the carbons have 4 bonds, none of which are multiple bonds, meaning double or triple bonds. You could say something like none of the bonds in all of the carbons have single bonds. Yes, all of the carbons have single bonds. You would say something like, none of these bonds can be decomposed because they're all single bonds. Yes. So in this one, for instance, we have this double bonded oxygen. We could break apart that double bonded oxygen and put on hydrogens instead. That makes this unsaturated. Do you see the difference? No, double and triple bonds would make it unsaturated because it is not full of hydrogens. Because you could do an addition reaction. Say I have ethene, for instance. If I added in H2, these two H's could break apart this double bond and pop it open and make this an alkane instead of an alkene. Okay, so that's 60. 61, explain in terms of molecular structure, as in you have to talk about structure, why the chemical properties of compound A are different from the chemical properties of compound B. So you have to talk about structure. Compound B contains oxygen. Compound A does not. Compound B is an acid with the COOH group. Compound A is not an acid. Compound B has a functional group. Compound A does not. Something to that effect, where you are talking about the structure. The structure is how it is built. Can you talk about the single double bonds? I don't know what you mean by that, Kate. Oh, okay. I thought you were asking me the question. I wouldn't just say single and double, because your grader might think that your single and double means your single carbon bonds, and then you are maybe talking about an alkene in here. I would be very specific that you had an oxygen. I would go a little bit deeper than to say they have different structure. I would explain what those differences were by saying that this has an organic acid functional group and this one does not. This one has double bonded oxygen and an OH, and this one does not. Don't go crazy. Like, you don't have to write a whole paragraph. One sentence is fine. Okay. A is a hydrocarbon and B is not. Yes, that would work. Okay. 62 to 65. Some isotopes of potassium are K37, 39, 40, 41, 42. The natural abundance and atomic mass of the naturally occurring isotopes of potassium are shown in the table below. Identify the decay mode of potassium 37. That is a reference table question, comes directly off the table. You just need to know where to look. The radioisotopes are on table N. Yep. On table N, it is telling you K37 has a decay mode. I'm sorry, I shifted this camera and it's a little hard to see. And now you're looking at my name. Okay. K37. And then up here, it tells you the decay mode. Sorry, the decay mode's up at the top. K37's decay mode is beta positive. You don't have to write it out. You could just put the symbol. Positrons, yes. I would just put the B+. I would just copy it directly off the table. But yes, the B+ are positrons. So that's it. Just reference table. Very simple. Then 36, complete the nuclear equation in your booklet for the decay of K40. Oh, shoot. K40 is not on the, whatchamacallit, table N. So I don't know its decay mode. So I'm just going to look up in the answer booklet and I'm going to write it for you right now. Okay. So here we go. K40, the nuclear equation is 4019K. And they write it like this. Ooh, it's not plus. Knucklehead. Plus blank. So that's the equation that's in the book. You are going to do the algebra. And this is like your 7th grade algebra. You are going to split the equation, top and bottom, like that. Positron, something really taught. Positrons is a real thing. It will be on the test. It's on table O. So 40 equals, that's what the arrow is, 0 plus a blank number. I don't know what it is. 0 plus blank. The blank has to be 40. So a 40 is going to go on top. And then the split, you have 19 is equal to -1 plus blank. Don't skip this question. It's algebra. Stop being a party pooper. -1 plus 20 will give you 19. Your 20 goes on the bottom. Then the next part of this, the part that makes this a part B, is that you have to go to the periodic table and tell me what this element is. Element 20, yes, it is calcium. I don't know what you missed from class that will be on the test. Everything's going to be on the test. Literally everything. Well, not everything's going to be on the test, but expect everything to be on the test. Okay. Yes, Jared, it is easy. Don't skip it. Haven't been here for 3 weeks. Don't care. You were here for all the other weeks. How did I know which decay mode to use? What was written in black was literally written in the answer book. Because potassium 40 is not... did it ask for K37? No, K37 was question 62. This is 63. K40, the decay mode is not written on table N, so this came out of the answer book. I just looked it up because I didn't know this off the top of my head. And yes, nuclear chemistry is pretty easy. I stick it at the end because it just shifts your thinking about chemistry, because I want you to think about the electrons the whole time. Okay, 64 half-lives, not my favorite. Determine the fraction of an original sample of K42 that remains unchanged after 24.72 hours. Okay. This is where things get kind of weird a little bit, where there's no like straightforward strategy for this. You just have to kind of like work with it every time. So these half-life questions, they could ask them in a lot of different ways. Sometimes they ask for the fraction. I'm just going to write. Sometimes they ask for the fraction. Sometimes they ask for the percent. Sometimes they ask for the number of grams. What else can they ask? I think that's about it. But they could also give you any of these and then ask you for the amount of time or the number of half-lives. Now, you guys haven't done... You learned this yourself over spring break. I never like exclusively taught it to you, but you are responsible for it. So they're asking, what is the fraction of an original sample of K42? So the way you're going to set this up every single time is going to change. It's all situational. This is going to be my fraction, and this is going to be the time, because they're asking me about the fraction and they are giving me an amount of time. So at time equals 0, I have 100% of my K42. 100% is represented by a fraction of 1 over 1. After 1 half-life, half of my sample is still going to be radioactive. And if I look at the length of a half-life of K42, that's going to be 12.36 hours. So the jump to get from 1 half-life is going to be 12.36 hours. Then in another half-life, we are going to have to add another 12.36, which is going to wind up giving me the 2472 that's asked about in the question. I had half of it being radioactive, and now I'm going to cut that in half again. So I'm going to have 1/4 of my sample is going to be left unchanged after 24.72 hours. So your answer has to be 1 over 4. It cannot be 0.25. It cannot be 25%. It has to be a fraction, 1 over 4. Lots of different ways they can ask these. You just gotta have to like go with the flow here. Had this been a percent question, you would have done 100% of your sample, 50% of your sample, and then 25% of your sample. If you started with 50 grams of it, then this would have been 25 grams, and this would have been 12.5 grams. Each time you cut in half. The important thing is that you always, always, always start with your time equal to 0. That's the biggest error. Because if you skip this, then you think the answer should be 1/2 and not 1/4. That's like the biggest error. I made this error for like 3 years before I realized that you're supposed to put time equals 0. So don't beat yourself up over it. Okay, 65 is calculating the average atomic mass for potassium. Somebody asked me to do this before, and I skipped it because I knew it was coming. So the way you determine, how do you know the fraction is 1/2? Because it's a half-life every time you cut in half. Which is why each of these, 100 to 50 to 25, you cut in half. 1, 1/2, 1/4, cut in half. 50, 25, 12.5, cut in half. Thank you. Okay, so 65. Show the correct numerical setup for calculating the atomic mass of potassium. In order to do this, average atomic mass is calculated a lot like your average in a class. I need a pen for this because it's a lot more detailed. Oh, I don't like blue pens. Ugh. Okay. So in class, I'll twist this back in a second. Your homework is worth 10%. So say the homework average is a 90, and that's worth 10%. And then we're going to add that to your lab grade. Say your lab average is a 95. We multiply that by the 20% for projects. Your test average, we'll say, is an 80. Multiply that by the 40%, blah, blah, blah. You do that. Then you do average atomic mass the same way. What happens is that this is a weighted average. Because your test average is worth more than your other averages, this affects your overall score the most. So if you have a low test average, you can assume that your overall average in the class is going to be closest to this. So we know that most of the potassium on Earth, like 93% of it, has an atomic mass of 38.96, right? The isotopic notation gives it a mass number of 39. So how this works, we are going to take mass, multiply that by the percent abundance, add that to the next mass times abundance plus mass times abundance plus mass times abundance, all the way until you get all of your isotopes covered. So here we are doing potassium 39. So K39, we are going to take 93.26. I'm sorry, 38.96. Multiply those two, add them to 39.96 times 0.01 plus 40.96 times 6.73. Take that and divide the whole thing by 100. That is the first option, where you just copy the numbers directly off the table and divide. We're dividing because these are actually percents, and you can't work with a percent. You have to divide it by 100. So this here is one of the valid answers. They don't care what the answer is. They just want the setup. The other option is that you divide each of these abundances before you plug them in. So you would do 38.96 times 0.9326. This 93.26 divided by 100 is equivalent to this number here. So you could do 39.96 times, you would divide this by 100. That'd be 0.0001 plus 40.96 times 0.0673. That's the other option. They just want the setup. Don't give them anything more than what they ask for. Everyone good with that? Mass times abundance plus mass times abundance plus mass times abundance over and over and over until you use up all your isotopes. Okay. Sweet. Okay, that was 65. So we have to remember that. Yes. It comes up on like every other test. This is like the one thing that they make you remember. Goodness gracious. The dog is running around upstairs. No, it is not on the reference table. You're just going to have to memorize it. I'm sorry. That's another thing that I dislike about Albany. They're a bunch of losers. Okay. Part C. Ooh, we're up to part C. Okay, so part C is going to be your chemistry applications. What happens is they are giving you more like real life situations. No, I'm not from Albany. Albany is the capital. Albany is where they make these tests. I hate them. So, the part C's are your real life applications. So what happens? This one is about the Bohr model. This is about some French dude with urea and ammonium rubbing alcohol. Then we have seawater. They give you some like real life stuff. Okay, so part C, the first thing we're looking at is this Bohr model. This paper is so freaking annoying. Bohr model of the atom was developed in the early part of the 20th century, 1911. The diagram of the Bohr model for one atom in the ground state of a specific element is shown below. The nucleus of this atom contains 4 protons, 5 neutrons. State the atomic number and the mass number. Okay. See, part C is supposed to be the scary part. This is not scary. This is easy. This is a question that I would very easily ask in class. If we have 4 protons, the atomic number is 4. The mass number is 4 plus the 5. That gives you 9. That's the whole question. Yes, the mass is 9. 4 and 9. Perfect. It is a lot. It's made to be scary. They give you all of this reading to scare you. The directions are here to scare you. It's a lot easier than you think it is. I promise. Number 67 says state the number of electrons in each shell of this atom in the ground state. So we know it's an atom, meaning we have to have 4 electrons. If we have 4 protons, we have to have 4 electrons in order for this to be called an atom. So we would have 2 electrons in the first shell and 2 electrons in the second shell. Nice job. Okay. 68. Using the Bohr model, describe the changes in electron energy and electron location when an atom changes from the ground state to the excited state. In order to do this, you have to know what these terms mean. This is the ground state. The ground state is where your electrons are the most happy. They're the closest to the nucleus. Hi. You want to say hi? Oh, I just ran over all the paper. Cooper, look right here. Say hello to everyone. There he is. Hi. Okay. I'll give you a better shot later. He's being disruptive. You're disturbing the learning environment. Okay. We have ground state. Goodness gracious, you're adorable. Best review ever. I'm so happy you're loving this. The ground state is 2 electrons in each shell. To go from the excited state, it's asking you describe the changes in electron energy. They're excited. They have gained energy. And when they gain energy, they drink a Red Bull, they go upstairs, right? You got 2 electrons here. You got 2 electrons here. You got 2 electrons here. What happens? These guys, you know, there's more shells. These guys get excited. They drink a Red Bull. They gain wings. They go up to other energy shells, right? It's usually like 1 at a time, but we can excite more than 1 electron. That's cool. So we excite an electron. It gains energy and it jumps to higher energy levels. That's it. Okay. That's all you'd have to say for that one. 69. Identify the element in, I guess I should read. In 1828, Frederick Wöhler, I don't even know who this guy is. See, this is it. They just like tell you irrelevant stuff. Can you fix the paper in the middle of the camera? Sorry. The dog ruined it. And I'm working in a mirror image, so I'm sorry. Goodness gracious. Let's just, okay. Okay, this dude produced urea when he heats a solution of ammonium cyanate. This reaction is represented by the balanced equation below. Identify the element in urea that makes it an organic compound. Okay, anything that's organic has to have carbon in it. Done. The answer to 69 is just the word carbon. Boom. Determine the gram formula mass of the product. There's something in my eye. Okay. No one cares. gram formula mass of the product. So for this, we have, we're just going to count. You start with the chart. Gram formula mass, knucklehead. We have carbon, nitrogen, oxygen, hydrogen, and you would sit here and count all of the atoms. So we have 1 carbon, 2 nitrogens, 1 oxygen, 4 hydrogens, right? That's my number of atoms. 4 H's, yep. And then we are going to find the mass of these. Carbon is 12, nitrogen is 14, oxygen 16, hydrogen is 1. Then we find the total. So 1 times 12 is 12, 2 times 14 is 28, 1 times 16 is 16, 4 times 1 is 4. Add up all of these. That's 20, 2, 3, 4, 5, 6. 60 grams per mole. That's the answer. Sorry, these papers are too long. Hold on, I'm putting it back, I promise. Okay, that's how you would do it. So we forever, for like the 2 weeks that we did math of chemistry, we always said start with the chart. This is your chart. Your chart is going to give you the gram formula mass, and then you would do all of your other types of math. Okay. So that is the gram formula mass. Determine the empirical formula for the product. So our molecular formula, the actual formula, is C imaginary 1, N2, O imaginary 1, H4. Now, the empirical formula is the most reduced version of this formula. Most reduced version of this formula is going to be this formula. You can't reduce it. That was a happy accident. They did not mean to do that. They meant for that to be a harder question. But that's what it turned out to be. Question 72, explain why this balanced equation represents a conservation of atoms. It was accidental. It's not actually a trick question. At least I don't think so. They, I think, are just stupid and didn't realize that it was easier than they intended it to be. Why balanced equation represents a conservation of atoms? There's a lot of ways you could write this. You could say that atoms are not created or destroyed. Same number of each type of atom on each side. You would say there's 1 carbon on each side, 2 nitrogens, 4 hydrogens, 1 oxygen, something to that effect. Just that there's a conservation of matter. For 73 to 75, rubbing alcohol sold in stores is an aqueous to propanol with the equation. Rubbing alcohol is available in concentrations of 70% and 91% to propanol by volume. To make 100 milliliters of 70% aqueous to propanol, 7 milliliters, blah, blah, blah. This is too much reading and I'm getting frustrated. That is done on purpose. They give you all of this information to scare you. They give it to you at the end of the test because you are burnt out and you are frustrated. Take a deep breath. I'm bringing candy tomorrow. You are going, once you hit part C, you are going to eat a piece of candy. You are going to wake up. You should even take a trip to the bathroom, go stretch your legs, take some air, get out of the room, stretch out. Part C is stressful. It's not hard, but it is stressful. So, state evidence that indicates the proportions of the components in rubbing alcohol can vary. You are not napping during this test. I'm going to have to bring the water bottle and spray you in the face. The proportions of this can vary because it is an aqueous mixture. Done. Aqueous mixture just means that it's mixed with water. You guys already know this. We've done this 1,000 times. Aqueous, aqua, it's in the word. Okay, 74. Identify the property of the components that make it possible to use distillation to separate 2-propanol from water. We already did this on this test. Distillation was an answer choice in one of the Part A questions. How does distillation separate stuff? Using heat, yes, but what property of the components? The boiling point, yes, perfect. The heat is going to get them to reach their boiling point, and their boiling point is what actually separates them. 75. Determine the maximum volume of 2-propanol in the 132 milliliter sample. This is a math question. Okay, we are looking at 2-propanol. Okay. In the sentence I skipped, in a laboratory investigation, a student is given a 132 milliliter sample of 91% aqueous 2-propanol, right? That's the information that we need to pull out. What's 73? State evidence indicates the proportions can vary is that it's an aqueous mixture. Aqueous means it's mixed with water. Okay, 475, we are doing kind of like an opposite of percent composition. It gives us the percent, which is 91, and it gives us the total volume. So if you remember, percent composition, we also did this on this test before, is part over whole times 100%. So this would be 91 times part over 132, well, 91 equals, times 100. Let me do this on bigger paper. Yes, Jared, go get some sleep. Go rest. I'm going to do the last 10 for those of you who want to stay. But if you got to leave and go rest, I 100% agree. You've gotten through, 90% of this test. It'll be just fine. I will see you guys in the morning. Rest up. Okay. You have your percent composition. Your percent composition was 91. Your part is what you're solving for. Whole is 132 and was multiplied by 100%. So to undo all of this, you would have to, this is multiplying by 100, divide by 100 to get rid of that, divide by 100. You get 0.91 is equal to the part over 132. Cross multiply. Throw that over 1. Don't be scared. You are allowed to do that. You get P is equal to 132, times 0.91. You're getting 120.12. Okay. This is telling you that this is the maximum amount of the 2-propanol that could have been in that 132 milliliter sample. The sample was 91% propanol and 9% water. So that's what it turned out to be. Okay. Whew. Last page. Last page. Okay. We're looking at a sample of seawater. And we have some ions here. We are writing the chemical formula of one compound formed by the combination of K plus ions with any one of these ions as water completely evaporates from the seawater. Oh, okay, that's not terrible. It sounds scary and confusing, but it's not. Chemical formula of one compound formed by the combination of K plus and any one of those ions. Now, potassium. We know potassium is a metal. Potassium is represented by K plus. It is a positive ion. It is only going to bond with negative ions. So we have a few to choose from. We can bond this with chlorine. We can bond this with sulfate. And that's all. So there's an easy choice and there's a not so easy choice. Well, a less easy choice. Sorry, I'm just trying to get this so I don't have to keep playing with the paper. Okay, there we go. So this potassium is K+, meaning it's K plus 1. Easy choice is Cl-. Crisscross, you're going to get KCl. Other option, K plus 1, SO4 minus 2. Remember, do not disturb the polyatomic ion. It is a bundle. You keep the bundle together. 2, just the 2, only the 2, not the negative, just the 2, comes all the way down and across. This 1 all the way down and across. You get K2SO4. If you choose to keep this in parentheses, no one is going to judge you. Okay, so those were the 2 possible answer choices for 76. 77, determine the number of moles of the SO4 2- ion in a 1,400 liter sample of seawater. Okay. This is represented in molarity, which is moles per liter. So we have molarity equals moles per liter. The molarity, we are doing SO4 minus 2. It's telling me that the molarity is equal to 0.028. I need to figure out the number of moles, and it's telling me it's 1,400 liters. Put that over 1, cross multiply. 1,400 times 0.028. I'm getting 39.2 moles. That's the answer to 77. Question, what do you mean, wait, what? I need a question. I don't get it. Okay, so they were asking how many moles of SO4 do you need or would be dissolved in the seawater? Why did I cross multiply? Because that's how you figure it out. That's just the math. So molarity is equal to moles per liter. You could also do molarity over 1 is equal to moles per liter. This was the only value I didn't have. When you have 2 fractions equal to each other, this part here is on table T. When you have 2 fractions that are equal to each other and you don't know one of the variables, yes, you can just put it over 1. Because it's a whole number. So a whole number over 1 is the same thing. If I put u over 1, you are still u. Okay. Glad that's cleared up. 78. Compare the radius of a magnesium plus 2 ion in the seawater to the radius of a magnesium atom. Okay. 2 things here. First thing is MELPS. Stupid acronym. No one has ever come up with anything good here. We have metals. Electrons lose. Goodness gracious. They become positive ions and their radii are now smaller. What happens? Magnesium has how many rings? 3? 4? I don't know. I've been doing chemistry for too long. Magnesium is in period 3, so it has 3 rings of electrons. It has 2 electrons in the valence shell. When magnesium loses these 2 electrons, it loses that shell. And then this is all that's left, is this one and this one. That's the reason it shrinks. It loses the 2 electrons, it loses the shell. So the ion is smaller. Yes, ions. Well, metal ions are smaller. the nonmetals are going to grow. I'll show you real quick. Nonmetals do the opposite of melts. What happens? Say we have fluorine, because she's easy. We have 1, 2, 3, 4, 5, 6, 7. Right? 7 electrons in the outer shell. What happens? If we add in another electron, these electrons, all 8 of them, are going to repel from each other, and they're going to repel and just take up like a tiny bit more space. Fluorine wants an electron really, really bad, so it's really easy for her to bond with other people or other atoms. So these 8 electrons are going to repel each other. Nonmetals are going to grow where metals are going to shrink. Do they put ionic radius in table S? No, they don't. You'd think I'd know that. Okay, so that was 78. 79. Using the key in your answer booklet, draw 2 water molecules in the box showing the orientation of each water molecule towards the calcium ion. So looking at the answer book, it tells you that a water molecule should look like Mickey Mouse, where the oxygen is white and the hydrogens are black. And then it gives you, this is, I'm copying it directly out of the book. This is what it looks like. You have calcium 2+, which is the same as +2. And it wants you to show this water molecule how it would look if it were frozen in time near this calcium. So calcium is +2. We know the negative end of the water is going to be attracted to the calcium. The question is, which is the negative end? So sometimes it's nice to take one of these like Mickey Mouse things and draw it the way we have been looking at it all year. Oxygen has 2 lone pairs that look like this. These lone pairs are the reason that they're Mickey Mouse ears and they're kind of like squished together. It's because these 2 lone pairs are actually like over here. And these 2 lone pairs, because they're not in bonds, they're a little bit wider than these bonds. And it pushes the hydrogens closer together. That's why water is not a straight line. I mean, this, don't draw that. Water is not a straight line because it has lone pairs. We know this. So the electrons are negative. We know this. This is your partially negative side. And in between your hydrogens is going to be your partially positive, which means your oxygen is going to be attracted to the calcium. This is your oxygen. You should draw it like this and put the hydrogens as far away from that calcium as possible. Does it have to touch the calcium? No, it doesn't have to, but it should be close. Like, don't put them in the corner of the box. Yes, you are welcome, Emily. Don't know who you are, but thanks for dropping by. Okay. Moving on to question 80. We are in the final 5. We are kicking butt here. We're almost done. My goal is to be done by 9:30 because I need some rest too, because I'm definitely having the anxiety for you guys. Okay. A scientist bubbled HCl through a sample of H2O. That means that they had water, right? They have a big sample of water, and they took a hose and like almost like the reverse of a vacuum, they took HCl bubbles and forced them into the water. They forced them in through the bottom because the bubbles rise. Okay, good so far. This process is represented by the equation below. Awesome. Scientist measures the pH of the liquid in the flask before and after the gas was bubbled through the water. The initial pH of the water was 7. The final pH was 3. Explain in terms of ions why the gaseous reactant in the equation is classified as an Arrhenius acid. So, scary. On purpose. Don't freak out. Take a breath. They want to know why the gaseous reactant is an Arrhenius acid. You know what a gas is. You know what a reactant is. You're going to look at the equation. These are your reactants. One is a liquid, one is a gas. Okay, the question is, why is HCl an areneous acid? Jeffrey, the Bronsted-Lowry says that acids donate protons. They're looking for the Arrhenius definition. So the Arrhenius definition is that this contains H plus ions. End of story. They literally ask for the word ion. Give them the word ion. Explain in terms of ions. Say the word ion. Contains H plus ions. Done. If this were Bronsted-Lowry, it would be a proton donor. Yes. Okay. What would be the color of Bromkressel green if it had been added to the water in the flask before any HCl was bubbled through? Okay. Before, the initial pH value was 7. So we're going to look, yes, at table M. What is the color of Bromkressel green when the solution has a pH of 7? So the way you read this, you are going to pick up your pH range and put it like literally on top of the color range. So Bromkressel green, I'm going to doodle it because I can. We have 3.8 to 5.4. It says it is going to be yellow and it is going to be blue. When you mix this, you have to know like first grade art for this. In between yellow and blue is green. So any numbers that are 3.8 or lower are going to be yellow. Anything 5.4 or higher is going to be blue. And anything that falls in the middle is going to be green. 7 falls over here. The solution is going to be blue. Literally, the answer is just blue. Okay. And this is like almost kind of a multiple choice question. Because if you look at the reference table, your only options are really like green, yellow, and blue. So there you go. Okay. 82. Compare the hydronium ion concentration of the solution that has a pH value of 3 to the hydronium ion concentration of the water. Okay. Hydronium is the other name for H plus. These guys are the same thing. H plus is the same as hydronium. If you remember from the pH scale, new sheet of paper. We did this earlier too. That was 0. That was 14. 7 is neutral. This is going to be blue because 7 is greater than 5.4. 5.4 and everything greater than that, all the way up to 14, is going to show up blue. Okay. Back here. pH scale. This is where we are going to have max H plus. This is where we're going to have like a little H plus. This is where we're going to have like almost no H plus. And it's almost no H plus. Because this is basic. This is acidic. Acid, base. It goes in alphabetical order. So when my solution has a pH of 3 versus, compare the hydronium ion concentration of the pH to the concentration of the water. So we are comparing the 3.0 to the water, which we know is 7.0. If I like drag these onto the pH scale, the 3 would be somewhere over here and 7 is literally right there. So the solution that has a pH of 3 is going to have more hydronium. Water is neutral. Yep. Water is neutral because you write the formula HOH, H plus, OH minus. They have equal amounts of both. So it is neutralized. So to answer 82, the pH of 3 would be more acidic, yes. and you would say the concentration of H plus is higher or greater, or there's more H plus, something to that effect. That's what makes it more acidic, is that there's more H plus in there. Everyone good? That was question 82. Um, 10,000 times, maybe. I don't know if it's 10 or 1,000. Either way, I wouldn't get into specifics on the test. They don't specifically ask you how many times. Because if you tell them how many times and your math is off, then your answer is wrong. Give them just what they want to know. Nobody gives you extra credit because you gave them more than they asked for. It would be cool if they did, but that's not the way it works. Okay. Moving on to 83. A small digital clock can be powered by a battery made from 2 potatoes and some small household materials. No one taught you about potato clocks, but you don't need to know potato clocks. You just need to know chemistry. They're going to ask you chemistry questions about potato clocks. Don't freak out. The potato clock battery consists of 2 cells connected in a way to produce enough electricity to allow the clock to operate. In each cell, zinc atoms react to form zinc ions. Hydrogen ions from phosphoric acid in the potatoes react to form hydrogen gas. The labeled diagram and balanced ionic equation below shows the reaction, the materials, and the connections necessary to make a potato clock battery. Potato clock would be really cool. Okay, the direction of electron flow in wire A as the 2 cells operate. Okay, so this is a redox. They are asking you which way are the electrons flowing. We know that they are going to move from anode to cathode. The anode is where oxidation occurs. The cathode is where reduction occurs. We know Leo says grr. When you lose electrons, we call it oxidation. When you gain electrons, we call it reduction. Another acronym, anox. And this isn't really an acronym. I don't know what they call this. Anox and red cat. Anode, oxidation, reduction, cathode. Okay. And we're always flowing from anode to cathode, from the loser to the gainer. So we are moving from zinc 0 to zinc +2. If zinc is becoming +2, that means zinc had 2 electrons, it was 0, gave them away, and now it's zinc +2, right? So zinc is the loser, which means zinc is the anode. So this would be zinc. And then it is going to go to the hydrogen. Hydrogen plus is becoming hydrogen 0. In order to do that, it had to gain negatives. So we are flowing from zinc to hydrogen. Okay. Write a balanced half reaction equation for the oxidation that occurs in the potato clock. The oxidation is happening to zinc because zinc is losing. The half reaction is going to show just what electrons are doing in terms of zinc. So we have zinc 0 is becoming zinc +2. We are balanced in terms of mass. Now we need to balance in terms of charge. So in order to get these to be the same, I'm going to put my electrons on the right. If they go on the right, My positive 2 and my negative 2 are going to cancel out. My overall charge on this side is 0. My overall charge on this side is 0. That's your half reaction for the oxidation. And 85, very last question. Explain why phosphoric acid is needed for this battery to operate. The reason for that, hydrogen ions from phosphoric acid in the potatoes react to form hydrogen gas. They are the electron gainers. Phosphoric acid is needed to absorb electrons. If the phosphoric acid weren't there, the zinc would be losing electrons to nobody. 83 is the zinc to the hydrogen. Anode to cathode. Phosphoric acid in 85 is going to be your electron receiver. And that is it, people. That is all 85 questions. Can you explain table J? Forgot how to read that. Okie doke, table J. Table J. 2 things on table J. Okay. Yes, we did it. We accomplished this Regents exam. Thank goodness. Zinc to the right. Yeah, you could write either left or right. That's fine. I guess you could also write clockwise. I wouldn't choose that because it's not really a circle, but clockwise would sort of indicate the right. So table J. On table J, it's telling you how active. So your most active metals are going to be at the top, which means these guys are the ones who want to lose the electrons. The ones at the bottom are the ones that don't really want to lose electrons all that much. They're not gainers necessarily because metals don't really gain, but they don't want to lose as badly as these guys. So these guys can be like talked into gaining electrons, right? So the way we read table J for voltaic cells like this potato thing is JAC, Jack. On table J, your anodes are at the top and your cathodes are going to be at the bottom. So any combination of metals, you are supposed to be able to figure out which one's the anode and which one's the cathode. So if we were looking at titanium and sodium, for instance. If you were looking at titanium and sodium, here and here, your anode is on top, your cathode is on the bottom. Here's your loser, here is your gainer. That's why they talk all the time about these lithium-ion batteries. Lithium is at the tippy top. Lithium is dying to get rid of electrons, makes very good batteries. Copper is a very, not a good gainer, but it's a bad loser. And if it's a bad loser, that makes it a decent gainer. So it happens like Duracell batteries have the copper top. All of these guys, copper, silver, and gold, they're pretty much interchangeable. They're all in group 11 on the periodic table. We call them coinage metals. Copper is the cheapest out of the 3. So you'll find that a lot of batteries are like a lithium, copper battery, because the further away they are from each other on table J, the better the battery. So you have your lithium, super loser, copper, bad loser, decent gainer. So that's where that idea comes from. Same thing with table J. You can also use this to figure out if a single replacement is going to happen or not. If it is higher on table J, then it will kick other elements out. So if I had, let's say, KCl and I don't know, fluorine. Fluorine is higher than chlorine, so fluorine will come in and kick off the chlorine for a single replacement. If you had KF and Cl, Cl is lower than F on the table, so this reaction won't happen because chlorine is not strong enough to kick off fluorine. Does that sort of make sense? Okay. For anybody who is going to have test anxiety and is not able to finish, like your brain just won't shut off, I am going to share a link with you, which is all about how to read reference tables. Hold on, just give me a second. Oof. Chemistry reference table. Let's see if this comes up. Okay, here we go. This is an awesome PDF from Garden City High School. It's like 14 pages long, but if you are interested in reading that, that is a good thing to read. This is going to tell you how to read all the reference tables, when to use the reference tables, all that jazz. And then there is a reference table video somewhere on YouTube. It's like an hour long, 57 minutes, something like that. That's definitely a good one to watch as well. What time is the test? We are starting at 9 a.m. It is a morning test. Every school kind of does it a little bit differently, but we're starting at 9. So I want you guys there like 8:30-ish. Yeah, reference tables need to be your very best friend. You need to like love the reference table, like SpongeBob and the marble. That needs to be you and the reference table. Yes, get there at 8:30. Could you write allows ions to move for 85? What'd I do with 85? I don't know. I don't know if that's a valid answer. Because the phosphoric acid is providing the hydrogen, but the hydrogen is providing the electron movement. I mean, I guess it could work. Yeah, because it is providing your hydrogen ions, which, yeah, you could write migration of ions. That works. Okay. That's it. That is all, people. Oh, boy. Amazon. Come on, Poppy. Okay. Go downstairs, Poppy. Okay, I'm showing you Cooper. Coopy, come here, honey. Come here. Can you sit? Okay. Heads up. Sorry for shaking you. Hold on. Reminder, I'm moving out of my classroom. So, my room is a disaster here. Coopy. Hi. Come here. Say hello. Say hi. He's so confused. Yeah, all this stuff from my classroom just wound up in the basement. Like all of it. The dog has an itch. He says hi. Can you stop being so itchy? Come here. Say hello. He's not really into this so much. Okay, bye, Coop. Okay, goodbye, children. I will see you all tomorrow. Go get some rest. If you don't, here's my philosophy. If you don't know it by now, you don't know it. So just accept the fact that you don't know it. You got your review already. Go to sleep. Go rest. Do something fun for like half an hour. Just watch the last minute of this video and focus on the dog. Hi. Hi. Bye, guys.